Afternoon. After yet another coffee break, and we have yet another session. And once again, as this is a cozy databases related corner, no exceptions. This is another databases talk. Well, and I'm really excited to invite here on stage Mons Anderson from Tarantool. And please welcome. A round of applause. So the stage is yours.
Thank you. Hello, everybody. My today talks is about reliability of in-memory. I often heard that in-memory is unreliable, and my today's talk is to break this idea. I am from VK, which mail.ru. I was a VK Cloud architect. I built an S3 in VK Cloud. I am Tarantool evangelist, architect, and product manager. I'm using Tarantool for more than 10 years, and I use it as a primary database. No backup, no fallback to some kind of Postgres, only Tarantool. So I know how to use Tarantool as a reliable database. Today, we will go through several steps, and if you have problems with seeing these slides, you can scan this QR code. There is the slides. You can look at them from your phones. I'll give it to you for about 10 seconds to scan the QR code. You may follow my presentation from your device. And today, I will show you how to understand this scheme. I will guide you through the step-by-step explanation of what is this. And to start, why in-memory database? The history of in-memory database, the history of databases started with disk storage. Today we know disks are slow. They have problems with performance. For a long time, memory was used only as a cache for disk storage. And some time ago, it was rather long time ago, almost 20 years, the performance became a bottleneck for disk-based storage. And there became the appearance of first in-memory solution. The first in-memory solution in-memory database I can find is times 10. I think it's a great database, great relational database, but it appeared too early. It was developed by HP, and it may be the killer of all Oracle. That's why maybe Oracle bought it. It's proprietary, and these days it's losing its position in the engine's rank. So first open source solution that's known as in-memory is Memcached. Please raise up your hand who used Memcache. Memcached appeared 20 years ago. It appeared in LiveJournal to support its growing, and it was used only as a cache. It was not a database, but that was already an in-memory solution. After that, there were several solutions, one by one, that were emerging in this market from different companies. And the basic question when you encounter in-memory is, why not to take my favorite MySQL Postgres and give it a lot of RAM? I take MySQL and give it a gigabyte of RAM. Will it work as an in-memory? No, it won't, because relational database, disk-based databases were developed in orientation to disk storage. Disk storage is slow. Disk storage requires optimization by I/O, but no optimization in space. And if you use your MySQL as an in-memory, it will consume 5 times more memory than relative in-memory solution. Working with memory quite different. When you access a memory, the memory reply is immediate for a process. If you query a disk and wait for response, disks are asynchronous. Access to memory is always synchronous. So memory is fast. And most of high-load applications of that days, when using common SQL solutions, were focused on only key value scenarios, because analytical scenarios are not for high loads. So when you need performance, you may choose in-memory. Today's in-memory solution can give you up to 1 million requests per second from a single core. There is a question, how does that happen? In-memory solution allow you to read from memory. Don't touch a disk for it, of course. And if you take your common approach, you perform one request, you make one operation with disk. And with in-memory, we take several requests and batch them in one operation to disk. If we take our good old scheme where we have an application and a database, we may found that database is not fast enough. And what we do, we put a cache aside of a database. This scheme is much more complex than those previous scheme where you have only an application and a database. And this cache can raise your performance by 10 times. But if you make a step further, you may find that if you use a database with in memory, it would be database, it would be reliable, but it would give you the same performance as a cache in the previous scheme, and this scheme is much simpler. Of course, this have a cost. And when we said about in-memory solution, they have the cost of everything in RAM. So your data must fit in RAM. And if you have a huge data set, you should put it into a memory upon database restart. So let's discuss a path from a database, from a cache to a database. In the history of Tarantool, Tarantool is a memory database. By the way, who knows or who heard of Tarantool before this talk? Very nice. Tarantool was called by different words. It's like memcache on straw, it's like Redis but better, it's database and an application server on board. Let's go through the brief history. First of all, Tarantool was like a memcache, just in-memory cache. But to solve the problems of cold start, it was upgraded to persistence. With persistence, it was enhanced then by replication. And the following step to create a database from it. What to do when you have several keys, several indexes, and one value? With classic, for example, memcache or Redis, if you have a key and a value, if you have several keys that point to the same value, you should create several key value records for those values. But you can merge them in a structure called tuple. It's like an array where all the keys consisted together, and then they following their value, and you have several indexes pointing those keys. It's like in a classic relational database, but in memory. So after that, Tarantool was enhanced with lower runtime that was later upgraded to cooperative runtime with event loop. And more later, an SQL was emerged in, and these days it's a cluster database on top of this, and have a built-in cooperative solution. And to highlight what differs a cache from a database is persistence, replication, and support for ACID and cluster. And if we talk about ACID, let's talk about how in-memory solution like Tarantool works with ACID. ACID is about atomicity, and atomicity is about operating on transaction like a single unit. Within a single core, we can easily treat several operations like a single unit, which is either commit or rollback. Within a single core and cooperative multitasking, we cannot care about consistency because transactions are executed strictly one by one. There is no parallel transactions. And that solves us the isolation problem. If there are no parallel transactions, that's no problem with isolation. And durability. Durability is about reliability of solution. And like all those classic relational databases, in-memory solution uses WAL, write-ahead log. Every transaction is persisted to non-volatile memory disk. When I set cooperative runtime, single thread, I set it's single. And transactions executed one by one, sequentially. Maybe this sounds a bit slow, but if we just measure the performance of a memory, we found that modern memory allows us to operate several millions of small read or write operations. And that does give about 1 million of requests per second. And those are rather fast. And without need to synchronize several cores, we now need synchronization primitives. So let's take a look how Tarantool works. All the data resides in RAM. Access to data is from a single thread. Data is accessed strictly through indexes. All the changes upon updates persisted through WAL, like in classic database. And consistent snapshot using only for speed up the start time. I'll show you this by the picture I noted above. There is a transaction thread. Within that transaction thread, there is a special memory allocator called arena. It keeps all the user data and all the user indices. To work with this within a single thread, there is an event loop which works with cooperative primitives called fibers. To communicate with user, there is another separate thread that didn't relate to data. It works only with the user. And all the changes are persisted to disk through a separate thread that operates with disk. When we need to take snapshot of our data to speed up our time, we just take a read view of the whole arena and dump it to disk. To operate with disk, we have a thread pool. And what is the key to performance? We have those syscalls, we have separate threads, we know that system calls are expensive, and the answer is batching. To make this system performant, we optimize the cost of every request. First of all, our network thread receives several requests from a user or users or clients. They are put into a buffer and they transfer into transactional thread within a single step and a single syscall. When we got a batch of updates that need to be written to disk, we put them together and within a single syscall transmit them into the wall thread. Those are syscalls, but it's like mass transportation. We have the cost for one request less than one syscall. That allows us to increase throughput. And of course, when we have access for it, it produces even without touching the disk. So let's return to the persistence of in-memory. Every write goes through memory to the disk. Writes are delayed, and reads always go into memory and never touch a disk. Reads guaranteed to be fast. Writes, of course, dependent on disk writes, but as we understand, when we put them together and we linearly update the disk, it's rather fast. So when we restart our in-memory solution, we must take all the data and put it into a RAM. So this would be rather slow. And that's one of the main costs of usage of in-memory database. You cannot just have cold start and use your data. First of all, you should take your data from the disk and put it into a memory. Then let's talk about the reliability of a disk. I said we write to the disk, okay, like other databases. Other databases like fsync. Who think that fsync is a must for a database? Okay, what's the purpose of fsync? There is a cache of operating system. Operating system not always write to disk, it writes to cache, and in case of power outage, those caches may be wiped without syncing data to disk. So fsync tells us flush those buffers to the disk. Okay, fsync protects us from power outage, but what about the disk itself? If you fsync your data, but then your disk broken, good luck, have fun. And after all, disk is not an only part. One may say, I use RAID. RAID protect me from the problem of disk failure. I will tell you a story. We had a server with 16 disks in it. They had RAID, and one power supply unit was able to kill 12 of them. So power supply units is a very good thing to kill disks in a RAID. After that, everything is put in a server. A server is put in a rack, in a row, and those all are connected to some data center power supply. It's okay if some outage by power supply would be temporary. And of course, everything is within a data center. And if someone thinks that data center is something reliable, data centers may burn with your servers. So fsync is okay. It flushes your buffers of operating system, but it doesn't protect from a lot of things that can occur with your system. So to protect your data from a single instance, you need replication. There were talks here about some kind of replication. Maybe I something repeat about it, but there is some consideration. If we took a pure in-memory system, like memcache, without disk persistence, and place it into several cloud providers, or not cloud providers, let's say it be 4 providers, 4 different providers, and they will replicate data, so each server provider will keep its own copy, and compare it to single, very good enterprise disk, the reliability of such a memory system with replication would be better. That's because of probability of simultaneous failure. The probability that Google and Amazon and DigitalOcean all fail at one time and wipe your data from RAM is very low. Let's consider a case. We have a probability of a failure in 50%. It's like, you know, the probability to meet a dinosaur, either meet or not meet. So 50%. It's kind of bad system with such a probability, but if we replicate it, the probability of the whole system will be better. The reliability of the whole system would be better. And if we take a lot of replicas, we can decrease the probability of total failure and loss of data to very small numbers. If we took not a 50%, but something smaller, that can be referred to the probability of data center to fail is something about 0.05%. Then the SLA for not losing your data reaches such dramatical small numbers that's even hard to understand. For example, the scientists declared the probability that humanity will die from a crash of asteroid as 1 to 10 million. So, let's consider a replication. If we have non-replicated system, in case of failure, we lose everything. We may have home system with several disks. We put all our photos to that disk. Someday, those disks goes wiped. You lose all your data. And if you keep a replica somewhere, you upload there to some drive, you will lose only latest data. In terms of system operation, that's called RPO, Recovery Point Objective, the point in time where we could get in case of failure. And with replication, the RPO of replicated system is equal to replication lag. If it's rather small, then you lose almost no data. Let's talk more about replication. The definition of replication is coming from biology, from replication of DNA, and it's about creating identical copies. In computer science, the purpose of replication may be different. It may be about protection from a failure. It could be in increasing availability, or it could be about scaling the performance for reading. And there are different kinds of replication many of you may heard of. There are synchronous and asynchronous replication. They play their role well. Someone said that synchronous replication or quorum replication is a must, but today asynchronous replication much more popular in real-world systems. Asynchronous replication have RPO greater than 0. It's about replication lag, but for most businesses that's much more acceptable than the probability of write failure for synchronous replication. And from the point of operation with master or leader, it could be single master or multi-master. Single master is a classic master and several replicas scheme, and multi-master is a complex scheme that requires conflict resolution and so on, but sometimes it is used. Let's take a look how replication could work on the example of Tarantool. Return to our scheme and recall that I already said that wall is replicated. Wall is a write-ahead log. So we put another instance of database, run a process called applier that connects to master. Master creates a separate thread that would relay those log, and applier will apply it to another process arena. That will follow the previous guide. The modifications would go through val thread into the val. It also may take snapshots, and the client may connect also to a replica as well. So the whole replication process looks highlighted now. To maintain the order of replication, used well-known log sequence number. Log sequence number, together with node ID, is the order and the place for every transaction occurred in a system. To explain how replication works and how same replication may be single master or multi-master, I will guide you through the following scheme. Let's consider we have single master. It has its own identifier equals to 1 and 0 log sequence number. When something updates, it increments log sequence number and write that to disk. When we have a replica, all those changes done to master is replicated as is with its own identifier and log sequence number to those replica. But each replica in such a cluster have its own log sequence number. And if we want to turn our system into master-master system, we just plug it as a master and allow it to increment its own LSN, to put those records into its own log, and to replicate them back. To maintain the consistency in such a system, used something. Who knows? Who is this? Not a lot. It's Leslie Lampard. In short, he is inventor of vector clocks. Vector clock is an algorithm, is a data structure that allows us to order some distributed system with distributed changes. I'll show it to you in a short. Every node have its own vector of changes. Changes created on this node put on its own component. And the superposition of all of these changes give us the up-to-date point. We just sum up those vectors to understand if we up-to-date or not, and which changes we should apply to make our database up-to-date state. So to finalize, the replication in Tarantool works based on write-ahead log. It uses vclock to define the state of replication, is it up-to-date or not. It may be master-master or single master. It may be connected via arbitrary topology. It may be full mesh, star, circle, and it may be both synchronous or async. It's configured per space. And to finalize, I will talk about MVCC. MVCC is multi-version concurrency control. It's the thing that allows us to operate with different transactions and different data sets. Let me remind you, I already said the persistence of in-memory is about writes are slow, they are writing all the changes to disk to be durable. So write is persisted to disk. After write occurs, it occurs in memory, and then it waits for it to be written to the disk. And naively implementation of in-memory database may read those so-called dirty data. It's not a dirty in terms of classic relational database, but I will show you what I mean by dirty. Let's consider a timeline. We have a memory and we have a disk. So our writer updates some record. The red cell with 0 is just a memory cell which we would update. We have a writer that update those cells and call a write to disk. It will eventually occur. Then we have a reader that came to our memory and read those values. After some time, read is confirmed, write is confirmed, and everything okay. Write transaction was succeeded. Then we read again the same value, and we have another writer, another reader that should read the data, and we encounter some disk failure. It may be simple disk failure everyone can meet. Disk is full. We cannot update our write-ahead log. We cannot persist our write transaction. It is okay, it is handled, so transaction would be rolled back and the following reads will read previous data. But we already have the reader that's seen the data that was rolled back. How we can fix that? We can separate the areas for readers and for writers. Writer writes to dirty area. Readers read only from clean area of already confirmed transactions. The transaction that confirmed when it's put into a disk updates reader area and we got fully consistent state. If something fails, it never appeared in the clean area, so readers always see good, clean data. We even more may enhance the system if we have synchronous replication. I will not to tell you about synchronous replication. It's very simple explanation, but if we not just wait for disk write, but also wait for replica, we will get something like synchronous replication. And this scheme works rather well, but there is a little problem. Every transaction has several states. With uncommitted transaction, no one can read the data, because if transaction is executing now, it exclusively works on a single thread, so no other transaction can see the data. But when update transaction says commit, it release those threads, so readers or other writers may operate in this environment. And for disk write or replica, we have confirmed state when the transaction was written to disk or replicated to another host. If we consider not just simple write, but read before write, and if we keep those reads from a clean area, we found such a case. First of all, we read from a clean area, then update something and write it to write back area. Everything looks okay until we meet several update transactions on the same data. When the second transaction tries to update its data on write area, it finds that data it was used to create the next record was obsolete. It was already updated. and that transaction conflicts with previous transaction, should be rolled back, and the transaction should be repeated. To fix this, there is an easy solution. It is unclear at the first step, but it really works. If we plan to make write modifications, we should read those so-called dirty data. So any write reads dirty data, then updates it, then write it, then updates it as a result. When we have a concurrent transaction, it will see already modified data that already enqueued into the write queue. And why this is not a problem? If we consider this picture, let's imagine that the first transaction will fail to write itself into a disk. Then, and only then, the second transaction may be considered as a data with as a transaction with dirty data. But the second transaction cannot be written after the failed second one, because if failed the second transaction, then all the sequential transaction would fail until the system is recovered. So the cause and its effect is may be considered clean with reading from a write area for write transaction. For read transaction, everything is okay. Pure read transaction must read from a clean area and always see committed and fully confirmed data. There is a little problem how to call such a kind of transaction when we want our read to read clean data and our writes seen the data I called dirty. We call it best effort. It's like in queues when we want some kind of ordering, but in several cases some reordering may appear. I'm coming to final slides. Let's finalize. Just to sum up. So how Tarantool works reliably? I said about reliability. Sorry. And Tarantool keeps all the data in a RAM. If your data doesn't fit in a RAM, you can't insert it into in-memory solution. All the data is accessed only through a single thread. In fact, only updates must be accessed through a single thread. Reads may be from a different thread because reads operates via read view. Data is accessed only through index. No full scans, no analytical queries, only something like key value but with multiple indices. Every change that we perform to our database is persisted via write-ahead log, just like any other classic relational database, with the same guarantees. ACID is provided by WAL, MVCC, and cooperative multitasking. Write-ahead log also used for replication to maintain the durability of data via replicated system. Consistent snapshotting used only to speed up the restart. We can turn off the snapshotting at all. I know that many of people think that snapshotting is a durability mechanism. No. Snapshotting is just a speed up. The main durability mechanism is a write-ahead log. And Tarantool has different variants of replication, multi-master, single master, synchronous or asynchronous that can be used according to your business needs. Thank you. Feedback are welcome. And I am ready to answer the questions.
Excellent.
No, seriously. I see no phones. You scanning QR codes. Please, I need your feedback. It's very important.
Thank you so much for doing my job, right? I had to announce that. Well, I'm happy. So seriously, please scan that, please provide the feedback, and now it's time for questions. All right, third row over here, please.
Hello, my name is Pavel. Thank you for enlightening talk. I want to ask you about what consistency models you assume for your system. Do you do synchronous replication without quorum commits and quorum reads? Do you test it somehow for these purposes or whatever?
For now, for these days, we have either quorum synchronous replication and also quorum reads. It just merged into the most recent update. We make tests similar to Jepsen. We tried to use Jepsen. We had several Jepsen tests, but we found that there is no ready test, that's only a framework, but we already have our own framework for distributed testing, so we adopt it for distributed testing of our raft, synchronous replication, linearizable reads, and so on. And for the Tarantool, the guarantee of transaction isolation always was serializable, and with linearizable read, it becomes linearizable. And you can choose which one you need. You may fall back to asynchronous replication if you need speed of operation with single master.
Okay, thank you.
Excellent, thanks. Right. Any other questions from the audience, please? Yes, I see somebody there in the middle.
Hi, thanks for the talk. Actually, I've got two questions for you. First, for me, it wasn't clear why should I prefer this in-memory database with persistent storage over my classic Postgres plus some Redis cache setup. And the second one, how do you resolve conflicts in like multi-master replication? Thank you.
Okay, if you use Postgres with Redis, that means that Postgres have not enough performance for you. Am I right?
Yeah, kind of. Let's, okay.
It didn't work. Okay. With Tarantool, you can just use it as a single database. You need no cache, you need no cache synchronization, cache expiration, cache eviction. You just use it as a Postgres in your previous scheme, but with much better performance. That's the reason. And the second question was about...
Yeah, the second question was how do you resolve
conflicts? For conflicts resolving, we have the ability to write a conflict resolution trigger. We have a rich runtime, which allows us to write functions using Lua, Rust, or C. And we have a powerful mechanism of triggers that allow us to catch the requests in different phases, including the phase of receiving a record through a replication. And it's up to user. We didn't offer some generic mechanism for conflict replication. We allow a user to define its own conflict replication mechanism. I know it's hard, but after all, building master-master system is rather hard. It's about consistency of your business data. So for those who required it, it's very good. For those who didn't require it, the single master mode is preferred.
Okay, thank you.
Perfect. Right, over there, left, right side of my room, third row over there.
Yep, right. Thanks for the presentation at first. Yep. And the question about scaling, you said you can't use Tarantool if your data don't fit in operational memory in RAM. So, for example, we started some application, the data fit, and at some point they stop to fit to the RAM. So usually we have to, buy a new server in cloud, because in disk storage we can add external storage and something like that, and with Tarantool we have to just buy more memory. And the first part question, and the second is consequence of that, because the RAM usually is much more expensive in clouds, and when it comes to compare advantage of performance to for much more money, maybe is there a comparison from you? Some comments on that part?
That's a favorite meme about if you are homeless, just buy a house. So in case of in-memory system, if you use in-memory system, you need its performance. If it's okay for you to use disk-based database, then you don't need in-memory. Or you may use in-memory only as a part of data. In-memory database is about the price of your data. In-memory is not cheap. And if it's a high price for you to pay for a memory, then your data is not so high in price, so valuable, yes. And I have in my own systems with several terabytes of RAM in a cluster, and after all, yes, about scaling. Yes, if we use single node system, we limited by a capacity of a single server, which for now is limited for about 2 terabytes of RAM. Our in-memory servers are now about 2 terabytes. And if we build big system and we plan to use it for more than 2 terabytes, we just use sharding. I did not cover sharding at all because I talk about reliability, how the data is persisted and recovered, not about scaling.
Right, perfect. Right, so of course, I was just intensely looking at our regular resident query in this room, and here he is. Right, so first row, please, over there.
Hi again. Classic question. As far as I remember, Tarantool is still written, at least the core is written in pure C, and your scripting language of choice for the business logic that you deploy within the app server is Lua, right? That's still the case.
No. It's now C and C++.
Yeah, like 10% of C++ or maybe 5%. Yeah.
And for those scripting, yes, Lua, and there are now a lot of Rust libraries.
And that's exactly the question. If you were to rewrite it from scratch today, what would you choose? Is it going to be, would it be still C plus Lua, or would you use, I don't know, Rust for the core and JavaScript for the scripting glue, or Rust everywhere, or what would it be? What's the biggest pain with, or in other words, what's the biggest pain with C and Lua respectively?
If you ask personally me, I'm very old developer that started from Perl for more than 20 years ago, and I like scripting languages. So in these...
Except Perl, of course.
No, including Perl. So in Tarantool, I choose Lua because it's very fast to develop something in Lua. When I have a lack in performance, I use C or Golang or Rust to build some small library that I plug into Lua. I know that someone prefer Rust for just starting with the Rust ecosystem, but eventually they fall into a problem that Rust is too complex to compile.
So what's the takeout? Okay, so you are tasked with creating a new in-memory grade solution today. You have full control over the languages. You have to choose a new platform. What's it going to be?
If I start from
Java, of
scratch,
course, right?
I think for these days the good solution for business is Golang.
Is it going to be performant?
Rather performant, it's suitable for business.
Okay, good enough. And for
But
scripting,
as for me, I don't like Golang.
all right. And for scripting, still Lua, right?
You need no scripting.
So why wouldn't you find this out in the continuation of this discussion in the hallway, just because we are running out of time and we still have one very important task to do. You need to select the best question that earns the prize.
I think it's about conflict resolution. The second question from
So
the guy in
who
the
raised
middle.
that about a conflict resolution? Do you remember? Anyone? I think over there, right? So the prize is coming your way. Right, and with this, thank you once again for the presentation and your insights. A round of applause, please, and coffee and
About scripting language.
yes, well, basically to continue that discussion in the hallway.
The best scripting language these days is TypeScript.